Next, I am pleased to introduce Chase Geigle, who's going to tell us about his exploration of automated grading of complex assignments, almost as if on cue from that last question, wondering about the complexity that this Spring method could handle. Chase.
Thanks. Okay. All right. So when I sat down to write this talk, I figured it might be good to approach it the same way that I sort of tell my undergrad students to approach reading research papers. Start by defining every word in the title. So I'm going to define every word in my title. So an exploration, in the sense that I don't have all the answers, I don't pretend to have all the answers, and I'm not completely solving the problem of grading complex assignments. Rather, my goal here is to sort of propose a couple different ways of looking at the problem, a couple different approaches that you might take, sort of contrast them, maybe argue that maybe one is better than the other, but I'll let you make your own conclusions. But I want to sort of propose ways of thinking about this. So this is just sort of seeing what this space looks like. And when I say automated grading, that's sort of, I think everybody knows what I mean, but let's be clear. I'm not designing a system where you can throw a brand new assignment at it that it's never seen before and it can automatically just say, oh, that's a 56 out of 77. Right? No, that's not happening. That will never happen. This is a machine learning approach, so this is actually probably something more similar to like semi-automated grading, right? So this is designing a system that learns from expert feedback or maybe non-expert feedback to try and predict grades. And what do I mean by complex assignments? So I'm going to try and define this by what it's not, and then sort of a complex assignment, in my view, and this paper's view, is going to be kind of what's left. So what's not complex is multiple choice. Right? Multiple choice is not complex, right? You either ticked the right radio box or you didn't, right? That's very easy to grade, and that's powerful, though, and you get pretty far with that. There are the physicists in my university that are doing education research get really, really far by only using multiple choice assessments for teaching physics, and they've shown that it's actually very, very effective. So it's not to say that, oh, you can't use multiple choice to teach anything. That's not what I'm saying. I'm saying that it is simple to assess, okay? I do think there are limitations on what you can teach with purely multiple choice, but you can get pretty far with it. But it's not complex. It's not complex to assess. Going a little bit higher up on that hierarchy, you have short answers. And I mean short answers, like most of the literature that's looked at automatically grading short answers is looked at things that are sort of a phrase, right? Like, where does the President of the United States live? The White House, right? You might accept White House, you might accept White House together as one word, you might accept White House with a dash, you might accept it with different capitalization, you might accept it with periods or commas or whatever, right? And typos, but more or less there is an answer, and the answer space is fairly small. Right, and you can do pretty well here. You can cluster things, and you can enable instructors to give grades on an entire cluster at once to try and help them scale. And I would say that you can get pretty far with assessing short answer questions. So I wouldn't call those necessarily super complex. They're more complex than multiple choice, but not incredibly so. An example of a complex assignment that I'm not dealing with here are programming assignments. Programming assignments are complex. There's lots of different ways to write a program that does a certain thing. There are, and in my experience there, even for a very basic programming assignment, students will surprise you with different ways of doing the assignment. I'm not focusing on that here. I'm looking more at assignments that are based on text. I'm not thinking about programming assignments, and moreover, the reason for that, I think, is programming assignments, there is sort of a nice way to do assessment there, right? Everybody sort of knows that you can unit test programs by, given this input, it produces this output, and if it doesn't, it's wrong. Right? And maybe, okay, you get more sophisticated than that. You have a battery of tests. You have some easy tests. You have some hard tests. You weight them differently, right? You can get even more advanced. You can look at, okay, what is the difference between this programming, this solution, and a couple canned solution to try and classify different kinds of errors that students are making, maybe weigh them differently, right? But that's not what I'm looking at here. I'm also not looking at essays. And the reason for that is I'm looking at assignments where there sort of is a right or wrong answer. Essays, most of the essay grading isn't looking at, is your argument right? Well, it's an opinion. Most of the time it's sort of persuasive essays, and there's not, your argument isn't right. Your argument is well-formed. Your argument is well-supported. You have, your argument is grammatically correct. Your argument has a flow through paragraphs, right? But it's not looking at, is the argument correct? I'm looking at assignments where you have text, you're making an argument, and the argument has a right answer. There is a right answer. Why? Okay? The motivating thing here is for teaching critical thinking. Okay, and I'm going to motivate this whole thing will be motivated by a particular case study, but the general class of assignments I think here are trying to teach critical thinking. You're trying to evaluate a thought process. How is a student constructing an argument? How are they reaching the conclusion that they reach, and does that conclusion match what an expert would reach, right? And in my particular case study here is veterinary medicine assignments, okay? So here your goal, and I don't expect you to read all this, I'm just giving you an idea of kind of what the assignment looks like, but the goal here is to assess whether a new clinician that you're training before they're in the clinic can make a diagnosis about a clinical situation with an animal, with a combination of some narrative around what's going on, what do you observe when you get there, so some sort of subjective stuff, but also concrete data like these are the test results, the pH of the blood is this, the red blood cell count is this, right? And so what we're trying to do here, and what they were trying to do in these assignments was assess whether or not the veterinary medicine students are constructing case analyses that are similar to and match up with what experts would say. And the way they do this is they have this applied learning platform that they use, and I don't expect you to read this, but this is just giving you kind of an idea of what it looked like, what the students were seeing. So over there is sort of the narrative, right, where that orange arrow, I'm using orange and blue, okay. So orange is coming from the narrative where they're selecting relevant passages of text. So this particular thing that I observed when I got there was important. Maybe the age of the animal was important, right? Or maybe what the eyes looked like was important. They were sunken in the orbits. Ooh, okay, that tells me something, right? And also, I'm also selecting some of the relevant tests. A lot of the tests won't be relevant, right? And an expert is able to quickly look at a chart and know which tests are important. This is the one thing I care about. This is the other, maybe these two things together tell me something, but everything else is irrelevant, right? A newbie probably says, well, all the tests are relevant, right? So they're building sort of what they think the important observations to make are. And then once they've done that, here's what they're building. So down here is a scaffolding, an outline scaffolding. So the form of the assignments that I'm looking at here are outlines. So the instructor has said, the argument should take a form that looks like this. Okay, just as a structure. It doesn't tell you how, but just gives you a structure. Right? And you are to fill in that structure with your observations, with your analyses. So this is combining text from the narrative and the test results with, okay, what do those test results tell me in my own words? What am I concluding from these? Why is that important? Okay, linking these together with maybe case studies that we've talked about in the class, or maybe from the textbook, or these sort of things, right? And their output is an outline that has bullet points that are labeled to tell me where they came from. So an O might be an observation, either from the narrative or a test result. An A might be an analysis or an answer that the student has. It's their own words that they've developed, that they've put in here. P might indicate some physiological thing that they're talking about, right? So there's these different bullet points that all indicate different kinds of information, and they're put together in some sort of coherent argument like this. Right? All right, and so I was brought in and I asked, okay, so how are these things currently being graded? What are they doing? The horribly unscalable thing that they're doing is having the instructor grade everything. Not a TA, because even the TA is hard to train to evaluate whether a student is an expert clinician when the TA is not yet an expert clinician either. Okay? And so these assignments were judged by the instructor on a number of different rubric dimensions. There's the full text there. I don't expect you to read that. I'll just give you the abbreviations. They're looking at sort of what the questions the student is asking to try and formulate their analysis. What kinds of answers are they providing to the questions that are in the scaffolding? What's the quality of their argument and the quality of the sources that they're using as the basis for their argument? Are their analyses correct? Right? Are the analyses that the conclusions that they're drawing from the observations right? Is their argument clear? Do I get confused while reading through their outline? Is it like they're talking about one thing and now I don't, what? How are these related? And the application of information from the other teaching materials into the assessment. Okay, and this is sort of mean and standard deviation of a Likert scale, 1 to 5, novice to expert for all of these, pretty tightly around 2 or 3, unfortunately. And this was for 107 assignments. So this isn't a big data set by any stretch of the imagination, but this is sort of a chicken or egg problem. We're not going to have a big data set for this because nobody knows how to grade it at scale. So you kind of have to at least show some promise. Okay, I might be able to do some of these things at scale before you actually have a data set at that scale for this. Okay, so these were sort of the research questions that I was asking when I started looking at this data. One was just feasibility of automated grading. Like, can I take state-of-the-art, off-the-shelf tools and just apply them directly to this problem? What happens when I do that? How close do you get? I mean, is that it? If that's it, great, right? But it's not, obviously, or I wouldn't be giving this talk. But I wanted to see, okay, just how good are they? I also wanted to think about, okay, there are a bunch of different ways to sort of formulate a grading problem as a machine learning problem. Which is the right one? Maybe there isn't a right one, but what are the different approaches and how are they different? Maybe one is better for different kinds of assignments than another. And then when you formulate the problem as a computation problem differently, you have to evaluate it differently depending on how you've designed the output of the system. So maybe you have to change your evaluation metrics. And then the last one was sort of integration. So what should this look like? Sure, I can sit up here and design a machine learning algorithm and I can make it give me outputs and stuff, and that's all great. But what does it look like if I deploy this thing? What should that interaction process look like? If I think about what does this, what is the teacher actually seeing? What is the grader actually doing? How are they providing the supervision to these supervised machine learning algorithms to make the whole thing work? Okay, there's a lot of stuff on this, so don't panic. I'm going to cover it fairly briefly. I have to thank Jose for giving a brief introduction to machine learning. Okay, the machine learning approach used here is one of those vector machine learnings, right? So you have a feature vector of a fixed dimension, and you have real values in those dimensions that indicate presence or absence or positivity or negativity of features, right? And then what this is comparing is for a specific rubric dimension. I just picked quality, you'll see why. I picked the quality rubric dimension for a specific rubric dimension. How does an off-the-shelf vector-based machine learning tool do when trying to predict grades on that 1 to 5 scale for this particular dimension? 4 different kinds of features. Okay, so the first line, these are similarity features. So I have an instructor-provided gold standard. This is what my expert analysis looks like. How similar is the student's assignment to that instructor assessment? Okay, and I had 3 different features for this. So this was across different bullet points. So how similar does the text of their analysis look like? How similar does the text of their physiological bullet points look like? How similar is it just in general, the whole thing? Okay, and that performs like it does there. The cell, so this is selection features. So now I'm looking at, okay, how selective is the student in picking sort of those observations to talk about, or those test results, right? And this is motivated by the newbie will pick everything and say everything is relevant, and the expert will find the one thing that's important, and that will be the only thing he selects. Okay? So this is looking at precision and recall of those tests that the student picks to incorporate into their analysis. Okay? TOCs is short for tokens, which it means for me unigram words. Okay, so single words. What are the words that they're actually choosing? What are the things that they're talking about at a high level? And then all is just throw everything together in one giant vector and use that as the representation. And essentially the numbers are evaluating MAE, mean average error, right? So absolute value of how far off it is, take an average, okay? And for this dimension, it does okay compared to a baseline. What's my baseline? So my baseline it was designed based on, okay, so I know that the grades are very heavily centered around 2 or 3. What if I just have it always say 2 or 3? It's not going to be wrong most of the time, but it's completely useless for grading. Everybody gets a 3. It's not helpful. Okay? So compared to a completely non-helpful, but sort of intuitively maybe doing decently in this kind of evaluation, we can beat it for this rubric dimension and for these features. If I switch rubric dimensions, everything fell apart. Okay, so now I was looking at, okay, what about the clarity of arguments? Is it confusing to read that outline? Right? Are they kind of constructing an argument that is easy to read, that makes sense? And my features don't really capture that at all. They're not looking at sort of, the things that you would look at in automated essay scoring, like do these paragraphs flow together? There aren't paragraphs here, but still there's bullet points that should kind of flow together, that should build some sort of cohesive argument. And obviously the features I've selected don't. Okay. So the main takeaway here is if you're just doing off-the-shelf stuff, your effectiveness depends greatly on the rubric dimension and the features that you use. So I took a step back. All right. Obviously, one approach is I could go down the rabbit hole of designing better features. I could start designing things that are specifically designed for the medical domain and not just assignments that happen to be, critical thinking rubric, critical thinking outline form. But I started to wonder: is outright grade prediction really our goal? And I'm going to argue that maybe it's not. Maybe we should think about automated grading slightly differently. And this is motivated by annotator agreement, first of all, which is low in practice, even for short answer questions. It was found that when grading on a sort of 1 to 5 scale for a short answer, 2 instructors, so actually people teaching the class, disagreed by at least 1.44% of the time. It's kind of rough, right? So if the annotator agreement is low, is it realistic to expect the machine to agree with us more likely than we agree with each other? Probably not. So there's probably a lower bound there, right, in the annotator agreement. And this is only going to get worse when we have more complicated assignments. As the rubric gets more complex, it's harder to get people to agree on whether this is a 3 or a 4 on a particular rubric dimension. And this is a significant barrier to leveraging peer grading. One of the things they had tried before they brought me onto this project was having peers grade using that exact same rubric. And of course, everybody said everybody was great, right? Because they don't want to, they're friendly, they don't want to hurt each other's grades, right? And also, I'm going to argue that that rubric was completely not the right thing to be giving students at all. Why would you expect a novice to be able to evaluate whether someone's an expert? Not going to work. The machine will also always be imperfect. It's always going to make mistakes. It's never going to be completely right. So how sensitive are you to making a small mistake? If the machine grades a 3 as a 4, that hurts you quite a bit, right? So is there a way that we can frame this so that when the machine makes little mistakes, it doesn't hurt us quite as much? And I'm going to argue that if you treat this as a ranking problem, not all of your problems are solved, but some of them are, okay? Annotator agreement. It's a heck of a lot easier to get people to agree, is A better than B? Then, okay, assignment A, is it a 3 or a 4? Assignment B, is it a 3 or 4 or a 5, right? This is really hard to get agreement on. Pairwise judgments is easy to get agreement on. When you have pairwise judgments, you can then construct a ranking based on the preference of what things should be above what other things. So now I can build a ranked list of all of the student assignments from best to worst. This also provides an easier way to leverage peers, I would argue, because now you can give the peer graders an easier problem. Is this better than that? Now, even if they think everybody is great, they still have to tell you which one's better. Okay? So their positivity, bless them, won't bias a pairwise decision. The machine will always be imperfect, so how sensitive are we to grading mistakes now? Well, if I'm building a giant ranked list, if I permute a couple items that are next to each other on the list, who cares, right? I'm probably going to grade by assigning cutoffs in this ranked list. And so, okay, if it's on a border, yeah, it hurt. Okay, but that's less likely than permutations inside of these grade boundaries, which don't hurt me as much anymore. If I switch to this, unfortunately, unless I have the gold standard where the cutoffs are, I can't translate it directly to MAE. So there's a different measure to look at here, like rank correlation measures. I'm looking at something here that is insensitive to ties, because if this machine permutes things that all have the same grade overall, it doesn't. I mean, it's okay, right? They're tied, so I shouldn't be hurt by that. And some ranking measures, you got to be careful, can hurt you in that case. So here's one that doesn't. You can see the paper for more details on this. This is basically looking at sort of how many pairwise things are permuted that shouldn't be. Okay. And I'm also going to argue, and this is more on the integration side of things, batch mode learning maybe isn't the right setup. So in batch mode learning, right, here is your training set. I give it to the machine, churn, 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 churn. Here's a model, and it gives me outputs, okay? Not collaborative, right? How do I pick the training set? How big should the training set be, right? None of those questions are answered using this setup. So it's not effectively maximizing the contributions that the instructor is giving the machine in the supervision. So instead, if you use active learning, not that kind, okay, active learning from like machine learning domain, right? where the machine is suggesting the next thing to label. So the machine takes some small subset of the assignments, learns a model, and then looks at your remaining data and says, okay, which ones of these am I really confused about? Okay, I don't understand this one, so please grade this one. This is going to give me the most information to my model, right? And that's what's happening here. If you do this, this is kind of collaborative by design. The graders are giving the machine feedback on the things that it's most confused about rather than things that it already knows. I already know that, don't tell me more, right? So the machine is helping you here, okay? If you do this and you look at that rank correlation, that distance measure, so smaller is better for this NDPM. If you look at, so random learning is that same process, but instead of picking the one it's least confident about, it just randomly picks one. Here's just a random thing out of the bag to grade. And active learning is picking the one that I'm least confident about, the one that I really don't know whether A should be above B or not. Okay? And when you do this, you more quickly converge upon a better ranking. Right? So I would argue that when we're thinking about these automated grading and machine learning problems, we should consider very heavily designing them in a way that active learning can be leveraged. Thanks.
Thanks, Chase. We have some time for some questions. Questions? Yeah.
Hi, I'm Minchul Kim from Drexel University, and your work was very interesting to me because I am very interested in open-ended learning and evaluating open-ended learning. And at the beginning of the presentation, you mentioned that there may not be a right or wrong answer in an essay. And I agree with that. And in open-ended learning, artifacts created by people can vary from individual to individual. But at the methodology, you employ experts grading for measuring the similarity between answers. So have you ever thought of how we can measure like the sophistication of an essay without expert labels?
Yeah, so that's an interesting problem, and I think this sort of goes back to thinking about annotator agreement, right? It's hard to, even with experts, it's hard to get them to produce the same artifact. So there's going to be multiple ways to approach the same problem, but you're going to end up at the same place. I think eliminating the expert feedback is probably very, very hard. I think one thing that may be promising is sort of to look at peer review heavily. And try and do calibrated peer review on that. But again, I think to do that effectively, you need to think very carefully, and if you get anything out of this talk, this is it, okay? If you're gonna do that, you need to think very carefully about the kind of question that you're asking the peer grader, right? If you're asking them a question that they can't possibly answer with high annotator agreement, it's not gonna give you any signal to any learning algorithm ever. If you can ask them a question that they're going to agree with each other on more frequently, then you can start to trust that more. So maybe if you can frame things as, okay, is A better than B, or some other similarly easy question, then you can trust the peer assessments better, even when they're not assigning an actual grade.
Hi, my name is Tim van der Zee from Leiden University. Thank you for your talk. I used to study clinical reasoning in physicians, so the specific case example was attractive to me. And what we found often is that for experts, how they reason, that the really salient characteristic is that they are not aware of how they reason. It's an automatic process because of all the training, because they are an expert, they don't really know what they are doing, even though they're really good at what they're doing. So I was wondering, is that to further improve methods like these, assessments like these, it is not enough maybe to rely on the overt knowledge that experts have about good reasoning, but to further study the underlying processes of expert reasoning and apply those characteristics to models like this, instead of relying on what experts think they are doing, because it's often different from what they are actually doing.
Yeah, I would agree with that. I think one of the things that needs to be done for sort of looking at these kinds of assignments where you're trying to teach some kind of thought process is you have to have sort of you have to get a step above. You have to sort of be metacognitive about it. Okay, what exactly is the thought process that they should be using? And you're right. Once it's automatic, they forget that, right? So I think the way to look at this is to sort of see how the student is creating the assignment. That's why they're collecting all this information on what observations they think are relevant at first, and what in the order they're filling in the bullet points and stuff. And I'm not using that log information, but that could be very useful to see how that changes from when someone is first in the class to when somebody is about to go into the clinic. And hopefully you start to see that process starting to converge more closely to what the expert is actually doing, not what they think they're doing.
The problem with ranking, I think, is the quality of the assignment between the first and the second student is, the difference is way, different than the quality of the assignment between the 50th and the 51st student. So how do you sort of, solve that problem?
Yeah, so this is sort of one of the key assumptions that underpins this, which is the assumption that you can provide a pairwise judgment more easily than you can provide a 1 to 5 rating for 2 individual assignments. If that's not true, this won't work. Right? You have to provide more pairwise judgments than you would have to provide actual grades for assignments. So I agree that it's probably hard to distinguish between 2 things that are right next to each other, but I'll also make the argument that maybe that's okay, because even if you permute 51 and 50, as long as the borderline between a grade A and B isn't right at 50, you're probably okay. It's more important that the ones that are good are more closer to the top and the ones that are bad are more closer to the bottom. And when you're doing the ranking, little mistakes you're a little bit less sensitive to it.
Just want to invite the next presenter to start getting set up, and we still do have time for a question or two. Ken, you raised your hand quite a while ago, so let's bring it up.
Ken Kadinger, Carnegie Mellon. It's kind of a clarification question. Your baseline method, the way you described it, it sounded like it wouldn't change based on the features if you're just using the high frequency category.
Yeah,
Can you say more why it's changing across the number of features?
Yeah, you can look in the paper for more details, but basically what we were doing there, because the data set's so small, I didn't use something like 5-fold cross-validation. We did a bunch of randomized trials of 50-50 splits, and so the data sets are changing between each one of those runs, and that's the difference. So it's just sort of variance in the training sets.
One more question? It's a click if you're right next.
When I'm marking as an educator, I take a lot of account of the fact that so long as I'm doing lots and lots of different assessments, they basically average out. And I know that when I do any individual thing, I get probably rubbish at even my own reflection. And so, but what's critical is not to have bias. So for instance, if I've got exam scripts, I'll always reverse the order between question marking to try and remove some of the bias that might build in. And I was thinking about, again, you could have, you had some pretty, in some sense, some of your trivial measures were pretty poor, but crucially it's whether they have bias in, is if you average that over the whole thing, particularly about these boundaries, maybe even some of your poor methods might have been good enough.
Yeah, I think it's understanding sort of why the annotator agreement is low, I think, is important. You can probably improve some of this by having multiple annotators or something, but I think, again, I think sort of the key takeaway is if we can frame the supervision for some of these things as easier questions that we're more likely to agree on, then we're better. So maybe if you're looking at providing an assessment for an entire test, if you can break that down to the problem level, maybe you can get better agreement on the problem level, but you don't necessarily agree on the, 2 instructors may give completely different grades for the entire test, but they're probably going to agree more likely on individual problems. Or maybe there are certain kinds of problems that you're more likely to agree on, and if there's no particular pedagogical reason to ask a certain kind of question over another, ask the one that you're more likely to be able to get valuable agreeing assessments on.
All right, let's once more thank Chase.
Oh,